Hi everyone. In this video, we present depth-aided visual inertial odometry system for RGBD sensors called DVIO. This research work was done at SOC R&D lab in Samsung Semiconductor Inc. by Abhishek Tyagi, Yangwen Liang, Shanshan Wang, and Dongwon Wei. Visual inertial odometry is a state estimation system that uses data from IMU and camera to estimate fixed-off pose of the body. VIO has become critical block for many augmented reality applications such as AR gaming, 3D reconstruction, and AR lenses. In recent years, we have seen an increase in the adoption of active depth sensors in mobile phones. The modern smartphones have sensors like IMU sensor, multiple camera sensors, as well as depth sensor. These depth sensors provide a good estimate of the scene depth in camera frame. This depth can be used to provide constraint for the camera motion, which will improve the overall performance of the VIO. In literature, monocular VIO has been well researched. WINS-Mono provides a very good implementation of nonlinear optimization-based monocular VIO. The system uses camera and IMU to perform the state estimation and is considered state-of-the-art. In case using depth sensor in VIO, WINS RGBD uses depth measurement only for feature state initialization, and DUI VIO uses GMM-based depth uncertainty model in a one-dimensional feature state. In all these systems, we observe a higher pose error and tracking failures. In our DVIO, we improve the performance by fully utilizing depth measurement for constraints in the optimization step. We also use depth measurement in case of unsynchronized RGBD and IMU sensor to better estimate the time offset between the two sensors. Finally, to improve the runtime performance of the overall system, we propose a block-based marginalization scheme to maintain real-time performance. In our DVIO, we use a sliding window nonlinear optimization-based framework, which is similar to the one proposed in WINS-Mono. The state vector is comprised of two sections. One is the navigation state XNav that has IMU pose, speed, and biases for every keyframe. And the second is feature state XFeed, which has feature state for the 3D landmark observed in the keyframe. We perform the state estimation by minimizing the cost function for sliding window using nonlinear optimization technique. The cost function has four components. First is the prior for the state from previous marginalization. Second is the IMU residue generated from IMU pre-integrate. These two residue blocks are computed using the same strategy as explained in WINS-Mono. The third component is the 3D vision residue, which is computed using 3D landmark estimated for the non-anchor frame using the VIO state. We use Cauchy loss function for computing the 3D vision residue. The fourth component is the feature state prior residue, which is computed using the feature state estimate and the feature measurement in the anchor frame. The 3D vision residue and the feature state prior residue is computed according to the feature state parameterization. In our DVIO, we have two types of feature state parameterization. First is the one-dimensional feature state parameterization. In this, the 3D landmark is defined in the VIO state using the inverse depth of the landmark in the first keyframe it is observed. Using the inverse depth and the 2D feature measurement in anchor frame I, we can estimate a 3D measurement of the landmark in non-anchor frame J. In non-anchor frame J, using the estimated and measured 3D value of the landmark, we can compute the 3D vision residue. In anchor frame I, the depth measurement from the depth map is used to compute the feature state prior residue. Next, we also show how to use three-dimensional feature state parameterization in our DVIO. Here, landmark is defined in the VIO state using the inverse depth and the 2D feature measurement in the first keyframe it is observed. Using the 3D feature state, we can estimate the feature measurement in non-anchor frame J and compute the 3D vision residue. In case of the anchor frame I, we can compute a full 3D feature state prior residue using the measured and estimated value of the 3D landmark. Here, we are able to generate stronger constraint using the 3D feature parameterization but this is also increasing the overall problem size. To compensate for the increased processing time, we propose block-based marginalization for faster processing. In the marginalization step of a VIO, we drop certain states from the sliding window to maintain the size of the problem. Here, we use the strategy of keyframe and non-keyframe marginalization as proposed in Wins-Mono. In the marginalization of the oldest keyframe, the size of the information matrix to be marginalized increases with the number of landmarks. This problem becomes 3 times when we go from 1D to 3D feature parameterization and affects the runtime performance of the overall system. In our DBIO, we propose a block-based marginalization, which performs marginalization of the block associated with all landmarks and then performs the marginalization of the block associated with pose, speed, and biases of the keyframe. In case of marginalization of the oldest keyframe, the information matrix of the marginalized state has a unique structure with sparse and dense blocks. In the image, the non-zero values are in yellow and the zero values are in blue. In our algorithm, in case of the block associated with the landmark, we have a very sparse matrix. We use this structure to efficiently marginalize the landmark from the state. In case of 1D feature state, this will be a diagonal matrix and its inverse can be easily computed. In case of 3D feature state, each landmark has 3 correlated coordinates. Hence, we compute the inverse of a 3x3 block and marginalize each landmark one by one. Once all the landmarks are marginalized, the dense block associated with pose, speed, and biases are marginalized. With our marginalization scheme, we are able to achieve faster marginalization processing time for both 1D and 3D feature parameterization. This enables the DBIO optimization thread to run at 10 Hz update, allowing for a real-time performance. In a scenario where we have unsynchronized sensors, we have a time offset between RGBD sensor and IMU sensor. This time offset is considered constant but unknown. To handle this problem, we propose to add time offset as part of VIO state. Using the 2D feature measurement and the depth measurement, we compute 3D velocity of the feature in camera frame. Using the 3D velocity and the time offset, we can propagate the feature measurement from RGBD clock to IMU clock. The VIO state, which includes the time offset, is then estimated by minimizing the cost function using nonlinear optimization technique. Here, the residue block from marginalization and IMU pre-integrate are same as in the synchronized sensor. The vision residue is computed using the feature measurement propagated to the IMU clock. With this, we are able to model the time offset estimation in DBIO, which improves the accuracy and robustness of our system. We evaluated the performance of our DBIO on a comprehensive test dataset. Here, we present our performance on VCU RVI benchmark. VCU RVI benchmark is openly available RGBD sequence dataset with a comprehensive test scenario coverage. As you can see from the table, our DBIO has best performance in 24 out of 27 sequence. Also, our system has least number of failures. Here we present a video showing the performance of our algorithm compared to other systems. First, on a synthetic sequence. Our DBIO generates superior point cloud. Next, in the VCU RVI sequences, one can see our DBIO performance is superior to other state-of-the-art systems. Especially in the long trajectory sequences, one can notice that our DBIO is able to maintain a very consistent pose. Our DBIO is able to return very close to the starting point of the trajectory loop also. To summarize, we have presented a method to add depth measurement from RGBD sensor in a nonlinear optimization-based VIO. We have shown that the depth measurement can be used in both 1D and 3D feature parameterization. Moreover, We propose a method to utilize depth measurement in the estimation of time offset for the unsynchronized RGBD and IMU sensor. In the marginalization process, we have also proposed a block-based fast marginalization scheme, which reduces the runtime significantly. Finally, we carried out extensive experiments to show that our proposed system outperforms the state-of-the-art in terms of reliability, accuracy, and runtime. Thank you for your attention.